Alright, in this video we're going to simplify some more complicated radical and rational exponent expressions. So let's look at this first one. I've got a couple radicals in the same problem. I got the square root of the cube root of 4y squared. So this looks complicated, but it's going to be a lot easier if I rewrite this into rational exponent form. A lot of the time things are easier to simplify in exponent form instead of radical form. So let's think about what this means. So square root of cube root of 4y squared. So I've got 4y squared. So what does a cube root mean? Well, a cube root means you're taking something to the 1/3 power. Remember, a cube root is the same thing as being taken to the 1/3 power. Okay? And then on the outside of that, I've got a square root. So what does a square root mean? A square root means I'm taking something to the 1/2 power. So what I have now, after writing it into rational exponent form, is 4y squared to the 1/3 to the 1/2 power. Okay. So looking at this, I can now apply the exponent rules that we should already know. So if I take a power to a power, what do? Well, a power to a power means I just multiply the powers together. So I have a 1/3 to the 1/2 power. 1/3 times 1/2 is going to be 1/6. So I can think of this as being 4y squared to the 1/6 power. Okay, 4y squared to the 1/6 power. So then what do I have? Well, 1/6 power is applying to both the 4 and the y squared, so I can take both of these separately to the 1/6 power. So what I have is 4 to the 1/6 times y to the, now remember, when you take a power to a power, you multiply. What's 2 times 1/6? 2 times 1/6 is 2/6. So y to the 2/6 power. Well, 2/6. What can I do with that? I can simplify it. 2/6 is the same as 1/3. So what I have is 4 to the 1/6 times y to the 1/3. Okay? And you can leave it like that, or if you want to, you could put this into radical form. So radical form would be the 6th root of 4 times the cube root of y. But either way is fine. If you want to leave it in exponent form, that's fine. Radical form, fine also. All right. So this next one, I got z to the -4/5. Okay. So I'm going to put this into kind of radical form just to kind of show you what's going on here. So I've got the negative exponent. So that means it's going to go in the denominator. So z to the -4/5 is like the 5th root of z to the -4th power. Okay, which is the same thing as 1 over the 5th root of z to the 4th power. Okay, now the problem here is if I want to rationalize the denominator is not rational because it's a root right now. So think back to how when we rationalize denominators, I've got a 5th root, which means I need a perfect 5th power. I don't have a 5th power, but I do have a 4th power. So I need one more 5th root of z in the denominator. So I'm going to multiply the top and the bottom by the 5th root of z to the 1st. Okay, so then if I do that in the numerator, that's all I have is 5th root of z. In the denominator, I now have the 5th root of z to the 5th power. And what happens to the 5th root of z to the 5th? What happens if you take a 5th root to the 5th power? Just cancels out. So now what I have is 5th root of z in the top over z in the denominator. Okay, so really all I did in this one is multiply the top and the bottom by one more 5th root of z so that I could make the denominator rational. All right, moving on, next one. So I've got x to the third, y to the fifth, to the 1/2 power times xy squared. Okay, now important thing to remember with all of this is the exponent rules don't change just because some of the exponents are fractions. Okay, so the same rules still apply. So when I take a power to a power, I'm still going to multiply just like I did in the other examples. So I'm going to do that. So I got x to the third to the 1/2. What's 3 times 1/2? It's 3 halves. So I've got x to the 3 halves. Okay, then I've got y to the fifth to the 1/2. So 5 times 1/2 is 5 halves. So I got y to the 5 halves. Okay, over here, there's nothing really to do right away because there's no power up here. So I'm just going to leave this as x y squared. Okay, so now that I've kind of simplified this first parenthesis over here, I'm down here, and now I can see, are there any other things I can do? Well, I've got these two have a base of x, so I'm going to be able to multiply those together, and this has a base of y, and this has a base of y, so I'll be able to multiply those together. So remember, when you multiply exponent expressions with the same base, you just add the exponent. So here I got x to the 3 halves, x to the first. Well, what is 3 halves plus 1? Remember, when you're adding fractions, you have to have common denominators. So instead of thinking of this as 1, think of this as 2 over 2. So then I've got 3 halves over plus 2 halves. 3 plus 2 is 5. So I've got x to the 5 halves. Over here I got y to the 5 halves times y squared. Once again, I want common denominators, so I'm going to think of this as being 4 over 2. So 5 halves plus 4 halves, I've got y to the 9 halves. Okay, and it's fine. You can just leave it just like that if you want to. If you want to put it in radical form, you could put it all underneath a square root. You could, and that would be fine. If you want it in the most simple radical form, if I write this out, what I have is square root of x to the 5th, y to the 9th. And then you are actually able to take some things out of that square root, because remember, you can think of this as being square root x to the 5th. There's 2 groups of 2 that go in there, because you can think of it as x squared, x, and there would actually be 4 groups of y that are perfect squares. So you could have y squared, y squared, y squared, y squared, y. Add all that up, you get to 9. So what you could finally finish off with is you can take out 2 groups of perfect x squares, so you have x squared on the outside. You can take out 4 groups of perfect y squares, so you have y to the 4th on the outside, and then left over on the inside you've got 1 x and 1 y that didn't have anybody to partner with, so they are unfortunately trapped still on the inside of the square root. Okay, over here I got z to the 2/3 over z to the 1/4. Now remember the rule for when you're dividing exponents if they have the same base, you can simply subtract the exponents. So for this, it's as simple as basically rewriting this to be z to the 2/3 minus 1/4. So how do I take 2/3 minus 1/4? I got to have common denominators. Common denominator between 3 and 4 is 12. So really what you can think of this is instead of over 2/3, think of this as being 8/12. And instead of 1/4, think of this as being 3/12. 8/12 minus 3/12 is 5/12. So I got z to the 5/12, and I would probably just leave it like that. Okay, so just remember, rules still apply even though there's fractions. You're dividing, it's at the same base, so you just subtract. Okay, so then over here, let's see, I've got lots of stuff going on here. I got x squared y to the 4th to the negative 1/2 power on top. I've got 81 x cubed y to the 6th to the negative 1 third power in the denominator. Okay, so there are lots of ways to go about doing this problem. Lots of orders you can do this in and still be correct. Okay, so what I'm going to do is I'm going to go ahead and right away, both of these fractions are to a negative exponent, which means both of them are going to move, okay, to the numerator or the denominator. So I'm going to go ahead and rewrite this to be 81x cubed y to the 6th to the 1/3 power in the denominator. So I get rid of the negative exponent, move it to the top, and I'm going to get rid of this negative exponent and move this to the denominator. So it's going to become x squared y to the 4th to the 1/2 power in the denominator. Okay, all right. Next, I'm going to apply my power rule. So I got 81x cubed y to the 6th to the 1/3 power. So all three of these things are being taken to the 1/3 power. So what I end up with is 81 to the 1/3 times x cubed to the 1/3. Now remember, when you take a power to a power, you just multiply the exponents. So 3 times 1/3 is 3/3. And then 6 times 1/3 is 6/3. So I've got y to the 6/3. Okay, now obviously I'm going to need to simplify that, but I'll do that next step. I'll do the denominator here quick first. So same thing, I got x squared to the 1/2. So 2 times 1/2 is 2/2. So I'm going to make that x to the 2/2. I got y to the 4th to the 1/2. So 4 times 1/2 is 4/2. So I got y to the 4/2. Okay, so I can keep going here. So first of all, 81 to the 1/3. Remember, 1/3 is the same thing as cube root. Okay, so are there any perfect cubes that go into 81? Or is 81 the cube root of anything? And 81 itself is not a perfect cube, but I can think of this as being the cube root of 27 times 3, because 27 is a perfect cube, and I'm going to be able to make this take the 27 out and make it a 3. Okay. Now x to the 3/3. What's 3/3 simplified? It's just x to the 1st. Y to the 6/3. What's 6/3 simplified? Well, it's just 2. 6 divided by 3 is 2, so I got y squared. Okay, and look what's going to happen here in the denominator. I got 2/2. Well, 2/2 is just 1, so I got x to the 1st. Okay, what about 4/2? 4/2 is just 2, so I got y squared. Okay, so what happens, I got x over x. Those are going to cancel out. I got y squared over y squared. Those are going to cancel out. So all I'm left with is this cube root of 27 times 3. Cube root of 27 is 3, so that's why we rewrote it like that. So I'm going to take the 3 out front. So I got 3 times the cube root of 3. So this whole thing simplified to just be 3 times the cube root of 3. Okay? Now, once again, the order doesn't really matter. You could have taken all of these to the negative half power and then canceled stuff out and then simplified, and you would have got the same thing in the end. So as long as you do the steps correctly in these simplifying ones, the order doesn't necessarily matter.